Welcome back to the Deep Dive. Today, we're jumping into really the fascinating, fast-moving world of generative AI and AIGC, that's artificial intelligence-generated content.
Mm-hmm.
We've gathered, well, quite a pile of sources for this one, research papers, articles on platforms like ComfyUI, really cutting-edge stuff.
That's right. And our mission, really, for you listening, is to pull out the key nuggets, provide those aha moments, help you grasp not just what these things are, but maybe more importantly, why they matter, why they're changing things.
Okay, yeah, let's unpack this then.
Yeah.
Generative AI, AIGC. What are we actually talking about here? Sounds, I don't know, a bit sci-fi, but it's definitely here now.
Oh, absolutely. It's very much here. So at its core, generative AI is a kind of deep learning technology. Its whole purpose is creating new, original content, multimedia stuff.
Right, creating, not just analyzing.
Exactly. Unlike AI that just processes data, this makes things. And AIGC is just the practical side of that, generating text, images, music, 3D models, videos, websites, you name it. The range of uses right now is, well, it's staggering. Visual arts, music, product design, even specialized medical stuff like 3D organ models for surgeons to practice on.
Really? Okay.
Yeah, and architecture, marketing, games, VR, the metaverse, manufacturing, it's cropping up everywhere. The key thing is this ability to create. It fundamentally shifts how we interact with digital tools.
That's a huge scope.
Yeah.
So, okay, what are the sort of foundational techniques? What makes this magic actually happen under the hood?
Yeah, the techniques are pretty sophisticated, but we can break down maybe 4 common ones. Generative Adversarial Networks, GANs, Autoencoders, Recurrent Neural Networks, RNNs, and Reinforcement Learning, RL.
Okay.
Let's start with GANs. You can kind of picture them as this adversarial duo, 2 neural networks basically fighting it out.
Fighting?
Well,
Yeah.
competing. You've got a generator network that creates new data, like an image. Then there's a discriminator network trying to figure out if that image is fake, generated, or if it's real.
Oh, okay.
And they're in this constant loop, right? The generator gets better at fooling the discriminator, and the discriminator gets better at spotting fakes. So they both improve constantly.
Pushing each other.
Exactly. Pushing the generator to make stuff that's incredibly realistic, sometimes, honestly, almost indistinguishable from human work. Which, raises some interesting questions, too.
Yeah, I can imagine. Okay, so that's GNs, this internal competition. What about autoencoders? How do they fit in?
Autoencoders work a bit differently. They're what's called an unsupervised learning algorithm. They basically take input data, compress it down into a sort of hidden code.
Compress it.
Yeah, like finding the essential features, and then they reconstruct it back into something really similar to the original. They're super useful for reducing data complexity, finding key features.
Okay.
A good example is in product design. They can learn the essence of existing designs and then, generate new concepts or optimize the ones you have. Really speeds up prototyping.
Interesting, okay. And RNNs. I feel like I hear about those with language stuff mostly.
You do, yeah. RNNs are special because they're great with sequences, things where order matters. They have this internal memory, you could say.
Memory.
Yeah, they can remember information from earlier in the sequence to help process what comes next. That's why they're so good for speech recognition, understanding language, even writing music sequences. They find those hidden patterns over time.
Got it. And the last one, reinforcement learning. You said RL. How does that work? Is that like AI learning from trial and error?
Precisely. RL is learning through interaction. An AI system tries things out in an environment, gets feedback like rewards for good actions, penalties for bad ones.
Like training a dog almost.
Sort of, yeah. Over time, through all that trial and error, it figures out the best strategy to reach a goal. It's how AI learns to play complex games or, control robots.
Okay, that makes sense. We've got these core techniques. But how does this all connect to something huge like ChatGPT? That's what everyone knows.
Right, good question. ChatGPT and similar models, they use a powerful mix. They're pre-trained on vast amounts of text, but then they use reinforcement learning, and this is critical feedback from actual human teachers.
Humans are in the loop.
Very much so. The process is called RLHF, reinforcement learning from human feedback.
RLHF. Okay, that sounds like humans are pretty involved then. Can you walk us through that? How does it work?
Sure, it's basically a 3-step process. It's quite meticulous. First step, data collection and fine-tuning. They actually hire people to write good answers to various prompts.
So humans write ideal answers first.
Exactly. They create this high-quality data set. Then they take an initial model, like GPT-3, and fine-tune it using this human-written data. Teaches it to sound more helpful, more human-like.
Okay, step 1.
Step 2. Reward model training. This is interesting. They use multiple models, the original, the fine-tuned one, maybe even human answers again, to generate different responses to the same prompt.
Okay, lots of options.
Right. Then humans rank these different answers
Mm-hmm.
based on things like, is it readable? Is it harmless? Is it actually correct?
Judging the quality.
Exactly. And this human ranking data is used to train another model called a reward model. Its job is just to predict which answers humans would prefer. It learns what good looks like.
So it learns to score the answers based on human preferences.
Precisely. Then, step 3, reinforcement learning. Now they take the fine-tuned model from step 1 and train it further using reinforcement learning. The reward model from step 2 provides the feedback signal.
Okay, so it tries to generate answers that the reward model will score highly.
You got it. It learns to maximize that reward. OpenAI uses a specific RL algorithm called PPO, Proximal Policy Optimization, for this part.
PPO, right? You mentioned that. Sounds technical. Quick explanation. What does PPO do?
Sure, PPO, Proximal Policy Optimization. Basically, it's a smart way to update the AI's policy, its strategy for generating answers. The key is proximal. It makes sure the updates aren't too drastic.
So small steps.
Yeah, kind of. It keeps the new policy close to the old one. This prevents the AI from suddenly going off the rails and making crazy changes. It leads to more stable, reliable learning and makes efficient use of the training data. Steady progress.
Okay, stable, efficient learning. Got it. So taking this broader now, how do these concepts apply to the really big language models, the LLMs we hear about constantly, like Google's Gemini, OpenAI's GPT-4? What goes into making those?
Well, those big names, Gemini, Meta's Llama, GPT-4, they all rely heavily on deep learning, transfer learning, and yes, reinforcement learning, often with RLHF. But training them, it's a massive undertaking.
Massive.
Think huge amounts of data that needs intense pre-processing, cleaning it, labeling it, splitting it up. Then you have to choose the right model architecture, how big, how complex. That dictates the computing power you need.
Which is enormous, I assume.
Enormous. And then you need sophisticated optimization techniques, things like stochastic gradient descent, atom optimizer, strategies like early stopping, adjusting the learning rate, normalization, all to make sure it learns effectively without wasting resources. It takes massive compute clusters and often months of time.
Right. Which brings us to something really interesting. This new player, DeepSeek. They seem to be shaking things up, suggesting maybe you don't need quite that much brute force. How are they different? Why are people calling their approach revolutionary?
DeepSeek is definitely one to watch. They're a Chinese AI company founded just back in July 2023 by Wu, and their focus is clear. High-performance AI, but cost-effective and, crucially, open source.
Open source is key.
It is, and what's revolutionary is how they achieve great results with less computational muscle. They use some really clever techniques.
Okay, like what?
First off, mixture of experts, or MOE. Think of it like having a huge team of specialist consultants. DeepSeek V3 might have, say, 671 billion parameters total. It's huge!
Yeah, huge!
But for any given task, it only activates a small fraction of them, maybe around 37 billion. It routes the task to only the relevant experts.
Ah, so it's not using the whole massive brain for every single thought.
Exactly. Traditional models use all their parameters for every task. MOE is way more efficient. It's not just saving compute. It potentially opens the door for smaller teams, open source projects to compete, democratizing it in a way.
Right. Selective expertise. Smart. Sarmiel.
Then there's multi-head latent attention, or MLA. You could compare this to a really smart note-taking system for the AI.
Okay.
Instead of trying to remember absolutely everything it reads in a long text, MLA helps it identify and hold on to only the most crucial bits of information in a compressed form.
So it summarizes the important stuff.
Sort of, yeah. It dramatically cuts down on memory usage. This lets the model handle much, much longer pieces of text or conversation without getting overwhelmed or running out of memory. More efficient for complex tasks.
Makes sense. Less memory clutter.
Then there's the idea of shared experts. Within that team of specialists, some experts handle the real fundamental stuff, common knowledge, basic language structure, things needed across many tasks.
And generalists.
Kind of, yeah. This frees up other experts to become highly specialized in niche areas without everyone having to relearn the basics. Boosts overall efficiency.
That sounds like a really logical way to organize knowledge in such a big system. Any other tricks up their sleeve?
A couple more key ones. Node-limited routing. This is important when the model is running on lots of computers networked together, which these big models often are.
Right, distributed computing.
Yeah. Node-limited routing sets up smart traffic rules. It limits which parts of the model network can talk at the same time, reducing data bottlenecks and speeding up processing when things are spread out.
Like managing highway traffic for data.
Good analogy. And finally, the FP8 algorithm. This is about how numbers are stored and calculated inside the model. FP8 is like a super space-saving format for numbers.
Smaller numbers, less memory.
Exactly. It uses less memory, but crucially manages to maintain high accuracy for the calculations. This speeds things up, especially on hardware that might have memory limitations.
Wow. So summing that up, it sounds like smart memory use with MLA, expert specialization with MOE and shared experts, streamlined communication with node routing, and fast math with FP8. It's all about efficiency. Why didn't we see this sooner? Why now with DeepSeek?
That's a really good question. I think partly some of these techniques like MOE were experimented with earlier, but maybe the tech wasn't quite mature or the implementations were too complex.
Right.
And honestly, for a long time, the focus in AI was just raw power, bigger models, benchmark scores. Efficiency and cost were maybe secondary concerns for the big labs.
A race for sheer scale.
Exactly. DeepSeek seems to represent a shift or maybe a catalyst. They're showing you can achieve top-tier performance and be incredibly efficient and cost-effective. They're making that balance a priority, and making it open source forces others to pay attention.
Right, pushing the whole field towards smarter scaling.
And speaking of smart learning, there's another related concept that's really important for efficiency: knowledge distillation.
Knowledge distillation. Okay, what's that?
Imagine you have a super experienced, brilliant professor that's your huge, complex AI model. And then you have a new teacher trainee that's a much smaller, more lightweight AI model.
Okay, professor and trainee.
Now, the professor trains the trainee, but instead of just giving the trainee the final right answers, the professor shares the reasoning. They provide soft labels.
Soft labels.
Yeah, it's like saying, well, the answer is likely A, maybe an 80% chance because of these factors, but B has a 15% chance because of this, and C is very unlikely for that reason. They share the probabilities, the nuances, the thought process.
Ah, so the small model learns how the big model thinks, not just what it thinks.
Exactly. It learns the thinking style, the decision logic,
Yeah.
and the benefit. It's incredibly resource saving.
Also,
You can train a much smaller model to perform almost as well as a giant one. This makes really powerful AI feasible on devices like, your smartphone or other portable gadgets.
yeah, so you don't need a massive server farm for every smart feature.
Precisely. Think real-time translation on your phone or smart assistants that run locally, protecting your privacy because the data doesn't have to leave your device. Knowledge distillation is kind of the unsung hero enabling that on-device AI future.
That's really cool. Putting powerful AI in our pockets, essentially. Okay, we've dug deep into language and learning. But the visuals, AIGC is famous for creating stunning images. How does AI do that? What are the cutting-edge methods there?
Right. Image generation is definitely one of the most visually striking areas. We touched on GANs earlier, that generator-discriminator duo creating and judging images. And autoencoders can be used, too, for things like compression or cleaning up noisy images. And you might remember older stuff like Google's Deep Dream making those trippy pattern-filled images. Or NVIDIA's StyleGAN, which got incredibly good at generating realistic faces.
Yeah, those were amazing.
But the current mainstream, especially if you want to generate an image just from typing text, that's really dominated by diffusion models.
Diffusion models, okay, I heard that term. What's the basic idea? How do they work?
At their heart, diffusion models work with probability. They see generating an image as like reversing a process of adding noise.
Reversing noise.
Yeah, imagine you start with a clear image and gradually add random noise step by step until it's just pure static. Diffusion models learn to do the opposite.
Start with static and take the noise away.
Exactly. They start with random noise like TV static, and then iteratively, step by step, they refine it, removing the noise according to patterns they've learned until a coherent image emerges.
Iteratively, okay. So it's a gradual process.
Very gradual. Many, many small steps. That's how they achieve such complexity and detail. The basic algorithm is 1. Initialization start with pure random noise. 2. Iteration in each step. Predict a slightly less noisy version based on the current state and what it's learned. 3. Creation repeat that iteration hundreds or thousands of times until you get the final image.
Wow, hundreds or thousands of steps. That sounds intensive. How do they connect that to text? Like a cat wearing a hat?
Great question. They incorporate the text description, usually converted into a numerical representation, into that iterative denoising process. So at each step, the model isn't just removing noise randomly, it's nudged towards removing noise in a way that aligns with the meaning of the text prompt.
Okay, so the text guides the denoising. That's clever. It sounds incredibly powerful, creating detailed images from just words. But are there downsides, limitations?
Oh, definitely. As powerful as they are, they come with challenges. First, as you guessed from the iterative process, training them is very resource intensive. Massive data sets, powerful GPUs, lots of time. That means high costs.
Right, expensive to build.
Second, generating an image can also be slow. All those iterative steps take time. It's getting faster, but it's not always instantaneous, which can limit usability for some applications.
Okay, not ideal for real-time stuff, maybe.
Potentially, yeah. And third, controlling the output precisely can sometimes be tricky. You might ask for something specific, and it gets most of it right, but maybe one detail is off, or it interprets your prompt in an unexpected way. Fine-grained control is still an active area of research.
Right. Getting it exactly how you pictured it can be hard.
Exactly. You know, it's almost funny. You can think of the diffusion model process like someone getting ready for a really important date.
Oh, yeah. How so?
Well, initialization is them waking up, maybe looking a bit rough. That's the random noise. Then iteration is the long process. Showering, picking clothes, doing hair, makeup, checking the mirror, adjusting details constantly. Trying to denoise themselves into the perfect state based on their prompt of looking great for the date.
Haha, okay, I see that.
Finally, creation. They look amazing. Perfect output achieved. Then they step outside, and it starts pouring rain. Back to a noisy state.
Huh. A very relatable model failure. Okay, so stepping back from the tech details, these tools are amazing, used in arts, design, even medicine, you said. But what are the bigger picture implications we should be thinking about?
Yeah, the broader impact is huge, and it's complex. There are definitely environmental concerns. Training and running these massive models, whether for text or images, consumes vast amounts of electricity that puts pressure on energy resources and contributes to carbon emissions.
The energy cost, that's a big one.
It really is. It makes the efficiency gains from things like DeepSeek's approach even more important. We need sustainable AI. Another issue is bias and accuracy. These models learn from the data they're trained on, right?
Right. Internet data mostly.
Often, yes. And that data reflects all sorts of human biases, societal biases, historical biases. The models can inadvertently learn and even amplify these biases. Plus, they can sometimes generate incorrect or nonsensical information they hallucinate.
Yeah, heard about hallucinations.
Yeah.
So we can't always trust the output.
Exactly. We need to be critical users. And then there's the impact on creative industries and content creation. AIGC is changing how things are made. Think AI writing news articles saves effort, maybe, but raises questions about job displacement, originality.
And quality. Can AI really be creative?
That's the million-dollar question, isn't it? Does
Right.
automatically generated content lack that human spark, that emotion, that unique perspective? It's something we're grappling with. How do we value human creativity alongside AI generation?
So putting this all together, what's the main takeaway for us listening? How should we navigate this future with AI, given all its power and its challenges?
I think the crucial thing is recognizing that this requires ongoing work. We need continued research, not just on capability, but on efficiency, on fairness, on controllability. We need smart solutions and, frankly, probably some thoughtful regulation or guidelines. It's about ensuring that AI development doesn't just chase raw power, but actively considers the social, ethical, and environmental footprint. We need to build AI that's not only powerful, but also responsible and genuinely beneficial.
What an incredible journey through this landscape today.
Right.
We really covered a lot, from the basics of generative AI and AIGC to the nitty-gritty of GANs, diffusion models, RLHF. We saw how DeepSeek is innovating for efficiency and understood that clever idea of knowledge distillation.
It's a lot to take in, and maybe a final thought for you to ponder. When you use AI, or even just read about the next breakthrough, try to think beyond the cool output. Consider the heading machinery, the immense energy it might be using, the subtle biases it might carry. It prompts a really important question, I think. How do we collectively steer this powerful technology? How do we ensure AI truly becomes a tool for a better, more equitable, and sustainable future, balancing all that amazing innovation with genuine responsibility?
A crucial question indeed. Thank you for joining us on this deep dive.